This is the review for test 4 of Math 136. Number 1, evaluate f times g of 1. So when you see this fg of 1, that's supposed to be multiplication, right? So it's just implied that it's multiplication. So this is going to be f of 1 times g of 1. So now if we look at the graph, f of 1, so f is this linear function. So we can see that for 1, that's going to be -3. And then g of 1, g is the parabola, and we can see that that point is -2. So then I have -3 times -2, so I get +6. For the given functions f and g, find the requested composite function. So f of x is x squared plus 7, g of x is x squared minus 5, and then we have f composed with g of x. So f composed with g of x can be rewritten as f of g of x. And then we can continue. G of x we can substitute in its explicit representation in terms of x, so x squared minus 5. And now for f, so that's taking the input and it's squaring it and adding 7. So I'm going to take that x squared minus 5. I'm going to square that, and then I add 7. So then multiplying that out, I get x to the 4 minus 10x squared plus 25 plus 7. So then it simplifies to x to the 4 minus 10x squared plus 32. Number 3, it says find the domain of the composite function f of g. So let's go ahead and find that. So we have f of g, or f composed with g of x, and you can think of that as f of g of x. So then this is f of 14 over x plus 3. And then f of x, so we take the input, put it over the input plus 7. So we have 14 over x plus 3 all over 14 over x plus 3 plus 7. Okay, so now if we look at either of these, we can see that x should not be equal to -3. We can see that in both of these places. And that's coming from the inside function, g. Now, if we look here, we can see that we have in the denominator this inside function, g of x, uh, and if this is equal to -7 anywhere, it's going to cancel out and make that 0. So we can go through and just solve this. And we get x is equal to -5. So then this part is giving us x better not be -5, because if it's -5, then we'll end up uh, dividing by 0 in that big denominator. So then the final domain, so we can either put it in set builder notation, and if you do decide to do it in interval notation, make sure that you have the numbers in increasing order so that it makes sense, like that. So either one of these are correct. And in some cases, I'll specify on the test which one. But if, as long as it's correct, I don't mind if it's one or the other, as long as it makes sense and it's technically correct. Um, let's see. That being said, I would prefer it if you demonstrated whichever way was requested. Now, notice I didn't actually simplify this because they were just asking for the domain. This was the quickest way to get it done. You could certainly simplify it, and I'm just going to finish simplifying as review. So if we're sitting here and we were also trying to find the simplified composite function, I'd one way to do this is I could multiply through by x plus 3 over x plus 3 in order to cancel out these. So this and this can go ahead and just cancel out. On the bottom, it's going to distribute. So up top, that's just 14 now. On the bottom, I have 14 plus 7x plus 21. And then I have 14 over 7x plus 35. And then let's see, up top, I can factor a 7 out. On the bottom, I can factor a 7 out. And then I have, these can cancel. And then finally, we see we get something that simplifies to 2 over x plus 5. So if you would have just gone through and simplified that, you can clearly see um, that that's just an alternative way. As far as which way is more work, it's kind of a wash, but not really, because you know that first way I did, you didn't have to worry about fractions as much, and I kind of skipped a lot of the work here just to make it fit. Um, Now this composite function that we end up with, so f composed with g of x equals 2 over x plus 5. If I just state it this way, um, it's not completely truthful. We also need to add on that x can't be -3, because when we go through that process of um, plugging everything in and simplifying, we lose that information as soon as we multiply through by this to cancel those out. Okay. Uh, F is one-to-one, find its inverse. In this one, there's no request to check. If there is a request to check, then you're expected to check, and that's worth points. But in this case, there is no request. So writing this in terms of X and Y, I have this, and then we switch X and Y. So then I have X equals Y plus 2 cubed minus 8. And then we're going to add 8 to both sides. We're going to take the cube root of both sides. Okay, so now we have the cube root of X plus 8 equals Y plus 2. And then subtract 2 from both sides. Then we have that. So then our inverse function is the cube root of X plus 8, and then all of that minus 2. And then you can certainly verify. So if we do F of inverse F of X, so then that's going to be F of the cube root of X plus 8 minus 2. So then we have uh, the cube root of X plus 8 minus 2. Let me just kind of, so then all of that is having 2 added to it, then it's being cubed, and then we're subtracting 8. So let's kind of work through all those layers. So that innermost set of parentheses, those can just go away. There's nothing to do with them. And then we see these 2's cancel. So then we have the cube root of X plus 8, quantity cubed, minus 8. So those cancel, and we have X plus 8 minus 8. And so the 8's cancel, and then we're just left with X. So then it works that way. If we check the other way, so then we have inverse F of X plus 2 quantity cubed minus 8. And then that's going to be the cube root of X plus 2 cubed minus 8 plus 8 minus 2. You can put parentheses around that. I'm just leaving them off because I'll get done faster. These can cancel. And then we have the cube root of X plus 2 cubed minus 2. So then the cube root and the cube cancel out. So I have X plus 2 minus 2. And then the 2's cancel out, and then I have X. All right. So those both checked out. That's how you check these if you wish to check. Um, if I don't ask for the check in the question. It's not required, but it is useful if you want to verify. But as you can see, it is a bit of algebra to do that. Okay. Determine the domain of the function, the range of the function, the domain of the inverse, and then the range of the inverse. Okay. So let's see. Let's go ahead and just set these up. So the domain of f, the range of f, then the domain of the inverse, and then the range of the inverse. Okay. So for f, we can just set the x minus 4 equal to 0, and we get x equals 4. So then the domain of f is x is any number such that x is not equal to 4. And then that gives us the range. Now, if I'm using set builder notation, I want to use y for my dummy variable in there. But otherwise it looks the same. Okay. Then what we can do is we can find the inverse. So now solve for y. So we have x times y minus 4 equals 1. So xy minus 4x equals 1. So xy is equal to 4x plus 1. And then divide both sides by x, and we have y equals 4x plus 1 over x. So then there's our inverse function. And then for the domain, we set x equal to 0 and solve for x, but it's already done. So now the domain of my inverse function is x is any number such that x is not equal to 0. Okay. And then now that gives us the range. And we just do the same thing, but instead of in terms of x, we just write it in terms of y. If you do it all in interval notation, then you don't have to worry about the xy representation. And then just a quick note. Uh, we have these relationships, and if you do write them in interval notation, it does kind of, simplify things a bit. And we can just write it like that. Now, it's still true if you're representing them in terms of x and y, because in the set builder notation, technically the variables are just kind of dummy variables anyways, because they're just representing a set of numbers. It's convenient to use x and y, though, when you're thinking about domain and range. Okay, so there's kind of the alternate version. Okay, use transformations to graph the function, determine the domain, range, and horizontal asymptote of the function. Okay. So we start with y equals 3 to the x. Then it's going to have 0, 1, 1, 3, and negative 1, 1/3. And I'm just going to do that as a dashed line. Okay. And then let's see, so to the negative x. So that's going to be a reflection across the y-axis. So far the horizontal asymptote is just the x-axis itself. Now when we add 2 for the final version, so everything is going to get shifted up by 2, including our horizontal asymptote. So now if it was y equals 0, now it's going to be y equals 2. And this is going to help guide you, oops, when you're sketching the rest of your curve. All right, so here's my final graph. Oh, that's not quite what I wanted there. Okay, so um, this horizontal asymptote, when it comes to an exponential function, is a wall that it's not going to cross. And if it helps you think about it, you can think about the fact that it's a vertical asymptote for its inverse function. And that's why the exponential function is not going to cross it. All right, so there's our graph. And you can see I have each transformation along the way graphed. I have the horizontal asymptote on there. And then I have, key points somewhat marked, but, I can be a little bit nicer and label them. So -1, 5, 0, 3, and this would be 1, and then 2 plus a third. So then that would be 7/3. Okay. So now what else do we want? So use transformations to graph the function. Well, that's done. Determine the domain range. So the domain, well, that's going to be all real numbers. The range, we can see that instead of 0 to infinity, it's going to be 2 to infinity, and I am not inclusive on the 2. Okay. Horizontal asymptote, we have y equals +2. Okay, that's all we needed. Okay, solve the equation. So x to the x, I'm sorry, e to the x to the x. So then these x's multiply, and that becomes e to the x squared times e to the 18 is equal to e to the 9x. So now, since these are multiplying and they have the same base, I can add the exponents and rewrite this as e to the x squared plus 18. And now that each side of this equation is just written in terms of a power of e, I can just set the exponents equal. So I have x squared plus 18 is equal to 9x. Subtract 9x from both sides. And now I have a quadratic equation to solve. So I have x squared minus 9x plus 18 is equal to 0. I can factor that. So I get x is equal to 6 and x is equal to 3. Um, you can check in the original equation with a calculator. Or you can play around with it some other way. Um, so my solutions are 3 and 6. Just those individual numbers. So I write them in curly braces. Okay. Number 8. Change the exponential expression to an equivalent expression involving a logarithm. So I have 32 to the 3/5 is equal to 8. Uh, now what we had, and I guess I'm going to write my y's slightly fancier now. So I have y equals log base a of x if and only if uh, x is equal to a to the y. So then we can go through here and say, okay, my x is equal to 8. So I'm just comparing. My a, the base of the exponent, is 32, and my y is 3/5. So then I have, let's see, so 3/5 is equal to log base 32 of 8. And there's nothing to do here other than rewrite it. Now, that being said, so I did the switch around like we did when we first introduced logarithms. Personally, here's how I would do it. So then here's my alternative approach. So I see the base of the exponent is 32, so I just do log base 32 of each side of the equation. These effectively cancel out, so then I have 3/5 is log base 32 of 8. Ta-da. All right. That's that's how I this is how I think about them when I'm asked to do these. I don't I don't do this. This is important to know, but kind of operationally, if I'm just doing math and figuring stuff out, and I want to change the exponential equation into a logarithmic equation or vice versa, I do something to both sides of the equation and think about it that way. Change the logarithmic expression to an equivalent expression involving an exponent. Okay, so now I have log base 5 of 125 is equal to x. And again, we have y is log base a of x. And let's see, well, we write this as x equals a to the y. Now, if we go through and just kind of compare things, unfortunately, um, my y is equal to x, my a is 5, and then my x is 125. So just, unfortunate notation. So then we have 125 is equal to 5 to the x. Okay. And then again, I'll just show that alternative approach again. So if I start from here, the way that we cancel out the log is to write each side of the equation as an exponent on some base. In this case, since that's log base 5, then I'm going to do 5 to the log base 5 of 125 is equal to 5 to the x. And then these effectively cancel out. So then I have 125 is equal to 5 to the x. And I hope you're sitting there thinking, oh, wow, that way's easier because at least to me, it feels easier. So I didn't have to worry about this stuff. There we go. Okay, find the domain of the function. Um, for a natural log, so if I have y equals any basic log function, so let's say this is f of x, or y equals f of x, then the domain is always going to be 0 to infinity, not inclusive on the 0. So in other words, if we put that in set builder notation, it's x greater than 0. So looking at this one, all we have to do is set the argument of the function, so the thing inside of the log, greater than 0. Just greater than 0. It can't be equal to 0. You can't plug 0 into the log. And then we just solve for x. So I have negative x is greater than negative 8. And then I want to cancel out the negative. So I'm going to multiply both sides by negative 1. So since I'm multiplying by a negative on both sides, I flip the direction of the inequality. So I have x is less than 8. So I have either this in the set builder notation or in interval notation. I have that. Okay. Solve the equation. I have log base 5 of x minus 3 is equal to negative 1. And I can just do 5 to the log base 5 of x minus 3 is equal to 5 to the negative 1, since each side of the equation is equal. And as far as setting them as exponents, exponents can be any real number. So these cancel out. So I have x minus 3. So 5 to the negative 1, that's just 1/5. So then I can add 3 to both sides. So I have 1/5 plus 3. That's 1/5 plus 15 over 5. So then I have 16 over 5. Okay. And you can verify this. So let's see if I have enough room on this page. So check. So log base 5 of 16 over 5 minus 3 is that -1. So then this is log base 5 of 16 over 5 minus 15 over 5. So then log base 5, and I have 1/5. Hey, and then, however you want to finish that out. Um, Here, I'll do something fun. Like you can either rewrite that using a negative exponent, or you can do this. You can use the quotient rule for logs. And then log base anything of 1 is always 0. And then minus log base 5 of 5, that's 1. Okay, and then you can see 0 minus 1 is -1. All right. The other way to do that without using a calculator is when you got to this point here, you could have also just rewritten it as 5 to the -1, and then the -1 comes down, and you have log base 5 of 5, and then that, oops, and then that just turns into 1, and then -1. Okay. All right. We got there eventually. So the solution is 16/5. With the logarithmic equations, the check is more necessary for checking for extraneous solution. So if you give me a solution that's not a solution, then that's not right. Okay, so watch out for extraneous solutions. They happen with the logarithmic functions. Okay, graph the function and its inverse on the same Cartesian plane. So we have f of x is log base 3 of x. So if we just have y is log base 3 of x, and then we swap x and y. So now I have x is log base 3 of y. Uh, then I can just put each side of the equation as an exponent on 3 to cancel out that log. So I have 3 to the x is equal to y, which is, of course, our inverse function. So the inverse of f of x is 3 to the x. Okay, so I just want to graph both of those. I also want to put in the identity function. Let's see if, hey, it was nice to me tonight. So y equals x. That's just useful for the symmetry. Uh, and to be honest, you get a more reassuring picture by the end. Uh, so now with either of these, you have these key values, and it may be slightly easy to remember with the exponential one, right? So if I plug in 0, it's 1. If I plug in 1, it's 3. If I plug in -1, it's 1/3. For the logarithmic function, you have 1/3, -1, 1, 0, and then 3, 1. And if we have it on there, and I see we do, we can go ahead and include 2, 9 and 9, 2, since we seem to have some space on there. Um, and then we're going to have a horizontal asymptote, y equals 0, and we're going to have a vertical asymptote, x equals 0. So horizontal asymptote, a vertical asymptote. Okay, our exponential function. Let's see, we have -1, 1/3, 0, 1, 1, 3, and 6, 7, 8, 9. So 2, 9. Okay, so that's my inverse function. And then for my original function, log base 3 of x, yeah, I'm just flipping those around. So let's see. So 1/3, -1, right about there. 1, 0, 3, 1, 6, 7, 8, 9, 2. Okay, and then there's f. Okay. And you can see that they're symmetric about the identity function y equals x. Okay, and that's all we needed for that one. Okay. Write as the sum and or difference of logarithms. Express powers as factors. Don't forget to do that part. Uh, the first step, maybe you want to rewrite those roots as exponents. Okay. And then everything on the top is going to be positive. And then everything on the bottom is going to be negative, with that log base 3 wrapped around it still. And then all of the exponents just come to the front as factors. Okay. And, if you don't want to put it on the line, you just want to put a box around it, that's fine. Expressed as a single logarithm. So I have 3 log base 6 of x plus 5 log base 6 of x minus 6. So first thing is to get all of my coefficients turned into exponents. Ooh, forgot my base 6. So plus log base 6. And that's to the 5. And then since these have the same base, I can rewrite these using the product rule for logs. So now, since these are being added, I can rewrite this as x cubed times x minus 6 to the 5th power, and then that's all inside of that log. Okay. Use the change of base formula and a calculator to evaluate the logarithm. Round your answer to 3 decimal places. Don't just straight up plug this into the calculator. I want you to write this down on a question like this, right? If I have log base 4.4 of 279, then I want to see you use the change of base formula with either the natural log or the common log. Okay, round to 3 decimal places. So I need to get a calculator. So to 3 decimal places, I have 3.801. Okay, so of course I'm looking for the correct answer, but I'm also looking to see that you've changed the base. Okay, solve the equation however you like. Uh, so let's see. So one way that I haven't done in class, well, no, maybe I have. I don't remember now. So I can get all of my logs on one side and then all of my non-logs, on the other side. So now I have log base 5 of x plus 4 minus log base 5 of x minus 3 is equal to 1. Uh, and it's important that they have the same base, right? Because next I'm going to use the quotient rule for logarithms, and I'm going to rewrite this as the log of the quotient of these things. So log base 5 of x plus 4 over x minus 3. Okay, and that's all equal to 1. And then you can either use that definition of the logarithm to change this into an exponential equation, or you can write each side as a power of 5. Okay, so then we have these cancel out, and I have x plus 4 over x minus 3 is equal to 5. And now I just solve this. So I multiply both sides by x minus 3, so I have 5x minus 15. And then I can subtract the 5x from both sides and subtract the 4 from both sides. So then I have negative 4x is equal to negative 19. And then x is going to be positive 19/4. And since I have a calculator open, let's check this using the calculator. So just for time's sake, I'm going to go ahead and just do this without using a change of base formula. And at least for the purposes of this course, I can see that these decimal expansions match. And that's one way of doing it. The other way that you could do this uh, is you can take these and subtract them and see if you get 0. Oops. Okay, so if I do it that way, you can see I get 0. So either way, I checked it. It worked. So checked with calculator. So X is an element of the set just containing 19/4 as far as the solution set is concerned. Okay, solve the next equation. I have 3 times 5 to the 2t minus 1, that's all up in the exponent, is equal to 75. I'm going to divide both sides by 3. So that, the way I wrote that's kind of weird. Let me fix that. There we go. So these 3's can cancel out now. So now I have 5 to the 2t minus 1 is equal to 25. And uh, I don't necessarily have to resort to using logarithms to solve this because I notice that 25 is 5 squared. So now I have 5 to the 2t minus 1 is equal to 5 to the 2. So I can just set the exponents equal to each other and then solve that resulting equation. So I have adding 1 to both sides, so 2t is equal to 3, and then dividing both sides by 2, so I have t is equal to 3/2. Okay. And then if you plug the 3/2 in, 2 times 3/2 is 3, 3 minus 1 is 2, so then I have 3 times 5 squared, and of course that's 75 for my check. Okay. How much money needs to be invested now to get $2,000 after 4 years at 8% compounded quarterly? Express your answer to the nearest dollar. So if we see compound interest. Um, and it said how much money needs to be invested now to get the $2,000. So they're giving us the future value of 2,000. We're actually looking for the principal value. And then they said, let's see, my interest rate is 8%. So that is 0.08. My time, they gave it to me in years, which is good. So it's 4 years. And it says compounded quarterly. So the number of compoundings per year is 4. And you can use the compound interest formula. And then the textbook has an alternative version. And you can get to the alternative version with a single step of algebra. If I multiply, if I either divide both sides or multiply both sides by something, so I could multiply it by the negative exponent version on both sides. And effectively what this thing is doing is it's dividing this thing out. They just cancel each other out. And it's using this, okay. It's using this property here. If I have a to the m times a to the negative m, it's equal to 1. Um, and this is just related to the property that a to the negative m is, 1 over a to the m and all that. So these wipe each other out. So then I have my principal value is this. And if you do use this formula, don't forget to put the negative exponent in. So I get to the nearest dollar, 1,457. Okay. Sanity check for this is if it's something that you're investing now to get, some higher dollar amount in the future, then what you're investing now should be smaller than 2,000. If you get an answer that's bigger, then it doesn't make sense. Maybe you forgot to put that negative exponent in there, or maybe you forgot to divide. The alternative version of this is, if you start from here and just plug everything in. Uh, let's see. Well, the inside of that's not so bad. That's this. And then you just divide both sides by that. So these cancel out. So then your P is 2,000 times 1.02 to the 16. And then you're still going to get this 1,457. Yep. Okay. Okay. If $5,000 is invested for 6 years at 5% compounded continuously, find the future value. The future value is A. So we're just using this formula, A equals P times E to the RT. Um, and we have P equals 5,000. That's what's being invested. My interest rate is 5%. So that's 0.05. My T is 6 years. So I have 5,000 times E to the 0.05 times 6. And this is pretty much a calculator plug and chug type question. Okay, so I have No, they didn't say where to round it, so if you're ever uncertain and you don't see it in the question, just round to the nearest cent. Okay. Because if you're thinking about it, well, that's the what the bank account's going to say in 6 years. Okay. If Emery has $1,800 to invest at 10% per year compounded monthly, how long will it be before he has $2,900? If the compounding is continuous, how long will it be? Oh, okay. So there's two versions of this. So there's the monthly. So we have P is 1,800. R is 10%. So that's just going to be 0.1. Compounded monthly means N equals 12. And then they're telling us the future value is 2,900. So then they're asking what our T value is. So for compound interest, it's A equals P times 1 plus R over N raised to the NT. So we know the 2,900, 1,800, 1 plus 0.1 divided by 12 to the 12 times T. So that's our unknown. Um, and what we can do, we want to get this T by itself. So I'm going to divide both sides by the 1,800. And then I can take my favorite log of both sides. So I'm just going to use the natural log. And the reason I'm doing this is to knock the 12t out of the exponent. Okay, and then to get the t completely by itself, I'm going to divide both sides by the product of 12 and then the natural log of 1 plus 0.1 over 12. So the 12s cancel out, and then this particular log cancels out. So then I end up with t is the natural log of 2,900 over 1,800 divided by 12 times the natural log of 1 plus 0.1 divided by 12. Round to the nearest, okay, so 3 decimal places, so to the nearest thousandth. So I'm getting 4.789. So then continuously, so we still have P equals 1800. A is going to be 2900. My interest rate, we are not changing that, so it's going to be that 0.1 again. But now continuously means that the n is approaching infinity. So we're using this formula A equals P times e to the RT. So then I have 2,900 is equal to 1,800 times e to the 0.1 times t. Divide both sides by the 1,800. And now when I take the natural log of both sides to get the stuff out of the exponent, well, natural log is base e, so these just cancel out. So now I have the natural log of 2,900 over 1,800 is equal to 0.1 times t, divide both sides by 0.1. And now I have t is the natural log of 2,900 over 1,800 divided by 0.1. Okay, plug that into the calculator. I get 4.769. So just it gets there a little bit faster. And then those are both years. Okay. The size P of a certain insect population at time t in days obeys the function P equals 700 times e to the 0.03t. After how many days will the population reach 1,500? So they're telling us that 1,500 is equal to the 700 times e to the 0.03t, and then we're just going to solve this for t. So divide both sides by the 700. Those cancel out. Divide both sides by the 0.3. And then we have t is the natural log of 1,500 divided by 700, and that's all contained in the log, and then that's divided by 0.3. So I have 2.54 approximately. Okay. Function a equals a naught times e to the negative 0.01386x models the amount in pounds of a particular radioactive material stored in a concrete vault, where X is the number of years since the material was put in the vault. If 300 pounds of the material are initially put in the vault, how many pounds will be left after 140 years? They're telling us that the A naught is 300. They're telling us that the T is 140. So this is basically plug and chug. So we're just finding A of 140. So that's 300 times e to the negative 0.01386 times 140. And I'm getting 43.09 pounds. Okay. Uh, so all of that was kind of just the Unit 4 review, and now we're entering into just the general review for the rest of the course. So this first one is solve in the complex number system. So I have x squared plus 4x plus 8 is equal to 0. I'm going to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So if you need to, a equals 1, b equals 4, c equals 8. So I have negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 8 all over 2 times 1. So I have negative 4 plus or minus 16. I'm sorry, the square root. Here, let me clean that up. Plus or minus the square root of 16. So 4 times 1 times 8. That's going to be 32. And it ends up being negative 32. So then negative 4 plus or minus, and then 16 minus 32 is going to be negative 16. And then the square root of negative 16 is going to be 4i, because what was inside simplified to a negative. And then I can distribute the 2 to each part. So I have negative 2 plus or minus 2i. And those are my solutions. So x is negative 2 minus 2i, or negative 2 plus 2i. And notice that they're complex conjugates of each other. It's just something to notice. All right, next. Find the real solutions of the equation. So I have a radical equation here. If it's a square root, the check is absolutely required. As soon as I square both sides here to try and get that x outside of the square root, I'm going to potentially introduce extraneous solutions. So now the square cancels out the square root. Okay. Uh, and if I'm taking x plus 3 times x plus 3, that's going to be x squared plus 6x plus 9, right? Because if you take x plus 3 times x plus 3, you have to FOIL it out. And then you'll have this x squared plus 3x plus 3x plus 9. Okay. All right. And then let's move things over. So now I have 0 is x squared minus 10x plus 25. And hey, if you notice it's a perfect square trinomial, then that's great. So then I see that x is equal to positive 5. And then I have to check. So I'll just put required. Check. So 16 times 5 minus 16 under the square root. Is this equal to 5 plus 3? So I have 80 minus 16. And then 80 minus 16 is 64. And the square root of 64 is 8. So I have 8 equals 8. So then my solution set is just the set containing 5. Okay. This is a U substitution problem. You can see the pattern. So we have x to the 6 plus 26x cubed minus 27 is equal to 0. That being said, uh, you are all fully equipped now to just use the rational zeros theorem and attack it that way. Uh, but if you notice the pattern where if you let u equal x cubed, then u squared is x cubed squared, which is x to the 6th. So, aha, it's following that pattern. So I can use u substitution and rewrite this as u squared plus 26u minus 27 is equal to 0. Now we can just look at that and see, oh yeah, that factors to u plus 27 times u minus 1. So then I have u equals negative 27 and u equals 1. And then we have to substitute back. So now this is x cubed equals negative 27 and x cubed equals 1. So then when we do the cube root of each side, um, so the cube root of a negative, that's fine. So then I have x is equal to negative 3. And then over here, if I do the cube root of each side, then I get x is equal to 1. And you can certainly check these however you like, either just plugging them in and doing the arithmetic, or we can just do negative 3 to the 6th plus 26 times negative 3 cubed minus 27. We get 0. And then, 1 plus 26 minus 27 gives us 0 if we plug in 1. Uh, so those are the solutions. So I have the solutions are x's that are elements of the set containing negative 3 and 1. And notice that if we had done the rational zeros theorem, um, it'd be 27 over 1, and we'd have 1, 3, 9, and 27 to check, and positives and negatives, and it just so happens that, oh, those are both in that list if we had done it that way. But this way is faster. Okay, solve the inequality, express your answer using interval notation. So I have the absolute value of x minus 4 plus 9 is less than or equal to 18. We want to get the absolute value by itself. And if it's a less than or equal to, then that becomes the sandwich, where you can rewrite that as -9 less than or equal to x minus 4 less than or equal to 9. And then you can work on each part simultaneously. So I'm adding 4 to get rid of the -4. And I have to do that to each section. So on the left section, I get -5. And then in the middle, I just have x. And on the right, I have 13. And it says express your answer using interval notation. So then that's going to be -5 with a square bracket, comma, 13 with a square bracket. Okay. Find and simplify the difference quotient. Okay, so f of x plus h minus f of x all over h. So f of x plus h, that's 6 times x plus h minus 4 minus the original function. Put that in parentheses. And then our goal with the difference quotient is to cancel the h on the bottom correctly. Okay, distribute. So I have 6x plus 6h minus 4 minus 6x plus 4. So then up top, the 6x's cancel, the 4's cancel, and then I'm left with 6h, I'm sorry, 6h over h, and then the h's cancel. So I get 6. Okay. The graph of the function is given. Determine whether it is even, odd, or neither. I see origin symmetry. So then therefore it's odd, or this implies that it's odd. Okay. You can all tell that says odd. Uh, use the graph to find the intervals on which it's increasing, decreasing, or constant. So increasing, decreasing, constant. Uh, so increasing, I can see it's from here to here. We can see that it's increasing. And then these are always x intervals. Uh, so this is increasing from -π/2 to +π/2. So from one x value to the other. Decreasing, I can see from here to here and from here to here. It's decreasing, so -π to -π/2, comma, not union, and then π/2 to pi. And there are no intervals where it's constant. So I will say that there are no intervals where it's constant, or just write none. So don't forget, increasing, decreasing, constant, you're using x intervals. So you're looking from x value to x value to tell the location on the function, or the span of locations on the function, where it's increasing, decreasing, or constant. Okay. graphs the function by starting with the graph of the basic function and then using techniques of shifting, compressing, stretching, and or reflecting. Uh, so we can see we're going to shift left by -1. Okay, and then the negative up front means reflect about the x-axis. The 2 is a vertical stretch by a factor of 2. And then the +4 is shift up by 4. Okay, let's start going through these. So my parent is just the square function. Y equals x squared. Okay. And then I'm going to do y equals x plus 1 squared. So then I'm shifting all of those points one to the left. Okay. Next, let's see. I'm going to, you could either do the reflection or the stretch next. I'll go ahead and do the stretch. So we're just multiplying all the y values by 2. I can kind of get them in the right spot. Okay. So if that's at 4, that's going up to 8, 5, 6, 7, 8. So we're not quite to the final one yet, but I'm just going to bolden that one in so because it's getting kind of busy up there. All right. let's see, use like a lighter color. And then next, I'm going to reflect. So that stays put. And then -2, -2, 5, 6, 8. Okay. And then finally, oh, we're getting to our goal here. So now I'm going to shift everything up by 4. 1, 2, 3, 4. 4. And looks like one of them disappeared on me. Okay. This is my final picture. Computer's starting to be a little uncooperative. We'll just make the best of it. Okay. Go away, little box. There we go. I feel ever so slightly better now that I got to just make that minor adjustment. There we go. All right. Find the vertex and axis of symmetry of the graph of the function. Uh, you could either use that -b over 2a formula, or you could complete the square. So then my vertex is -3, -1, And my axis of symmetry is, it's an equation. Ooh. X equals this X component of the vertex. So X equals -3. Okay, solve the equation in the real number system. So I'm going to use the rational zeros theorem to maybe come up with some guesses, or if we look at that, I don't need to use that after all. So if I look at the greatest common factors of these two groups and use factor by grouping, x squared times 3x minus 1 minus 5 times 3x minus 1. Factor out the 3x minus 1. And I have x squared minus 5. So then I can set each one of these equal to 0 using the zero product property. So then 3x equals 1, x equals 1/3, x squared equals 5, and then the square root of both sides. Don't forget, when you actively take the square root of both sides, you have to put that plus or minus in. So I have x is plus or minus radical 5, x is 1/3. So now the solution set is negative radical 5, and 1/3. Now, if we would have used the rational zeros theorem, we would have been perfectly fine. We would have found at least one rational zero, which is the 1/3. Uh, but you would have been, let's see. So 1, 5, and 1 and 3. So you would have had plus or minus 1, plus or minus 5, plus or minus 1/3, plus or minus 1/5. So you would have had 8 guesses to work through, and you would have gotten to that positive 1/3 eventually. And then once you've find the depressed equation, uh, it would have just been a quadratic uh, to solve. Find the domain of the rational function. Nothing fancy, just take the denominator, set it equal to 0, solve for x. Don't forget, if you're taking the square root of both sides, to put the plus or minus in. So now, if we're talking about domain, these are values that are not in the domain because they would cause the expression to be undefined. If you use interval notation, make sure you go in the increasing order. If you use set builder, it's maybe a little bit easier to express these. So either way. Find the vertical asymptotes of the rational function. Is it in lowest terms? Well, let's figure it out. So the top looks fine. It's x minus 7. Downstairs, there's a lot of stuff going on. I'm going to move stuff around a little bit just to make it feel a little bit more comfortable. And I'm going to factor off negative x. So I have negative x times x squared minus 49. And I see that's the difference of two squares. So the difference of two squares factors to x minus 7 times x plus 7. And I can see that these cancel each other out. So f of x can be rewritten as 1 over negative x times x plus 7, or maybe a little bit nicer, 1 over, or negative 1 over x times x plus 7. And then we need to state that we're not allowed to plug in a positive 7, and that's based on the original version of the function. Uh, if you plug in positive 7, then you'll be dividing by 0. So that's why we want to make that statement. But now that we're here, for the vertical asymptotes, we're just going to set this x times x plus 7 equal to 0. So then we get x equals 0, and then x plus 7 equals 0, so x equals negative 7. So now the vertical asymptotes are x equals 0 and x equals negative 7. So these are equations for vertical lines, so make sure you write x equals 0, x equals negative 7. Okay, solve the inequality. All right, so we have real zeros, and then their multiplicities. So I see we just have one real zero of positive 2 that has a multiplicity of 2. Then we want to figure out where it's undefined and what the multiplicity of that is. So call this f of x. So then the top is factored, the bottom, that's the difference of two squares, so we can factor that and rewrite it as x plus 6 times x minus 6. So we can see it doesn't cancel or anything, so it's already in lowest terms. And we have it being undefined at positive 6 and at negative 6, and each one of those has a multiplicity of 1. All right, so now we're going to use those values to divide up the number line. And we can see we have a strict inequality, so we don't have to worry about any or equal to's. But remember, it's that value on top, where we have that real 0. That's the only thing, if it was a non-strict inequality, where you would use that square brace, or include that value in the final solution set. Okay, negative 6, 2, and positive 6. Now I'm going to mark these with open circles, because none of these are going to be included because of the strict inequality. And then test value, how about, let's go ahead and just use 1, or let's use 0. So we're going to test f of 0. So we can do 0 minus 2 squared over 0 squared minus 36. So then that's going to be 4 over negative 36. So that's negative 1/9. And the really important feature here is that it's negative. So then that means it's less than 0. And we mark this region with a negative value. Okay. Uh, since where it's undefined, um, each one of those has a multiplicity of 1. So if we go to this negative 6, it's supposed to have an opposite infinity. So since this entire region from negative 6 to 2 is negative, then that means the opposite infinity is going to be plus. When we go to the 2, since that has a multiplicity of 2, that means it's actually touching at the x-axis. So the sign's going to stay the same. So that's going to be negative. And then when we get to the positive 6, it's an opposite infinity. So then that region is going to be positive. Now, that's just the shortcut using the multiplicities. You could certainly also just go in with additional test values and just test all of those. So f of -7. So we'd have -9 squared over -7 squared minus 36. So we'd have 81 over 49 minus 36. So 81 over 13. And that's positive. Well, how about that? It matches. F of 3. So we're going to have 1 squared over 9 minus 36. So we have 1 over uh, negative, uh, hang on, I can do math in my head. 27. So it's -1/27th, and then the important idea there is that it's negative, and oh, hey, I already marked that negative. And then f of 7. So then that's going to be 5 squared over 49 minus 36. So we have 25 over 13, which is positive. And see, that's already marked positive, right? Um, I forgot to label these regions. So this was -infinity to -6, -6 to +2, 2 to 6, and 6 to infinity. And we wanted greater than 0. So we have just the plus ones that we're interested in. So then my final solution is going to be -infinity to 6 union, I'm sorry, to -6. Okay, come on. Go away, stray mark. To -6 union with +6 to infinity. And, these weren't involved. All right. Do we have anything else? All right, that's it. Um, good luck on test 4, everyone.